Okay, gang, today we are going to work on the next section, that is the following section. Section 1.2, Analyzing Graphs of Functions and Relations. So, to expand on what we were doing previously, we are going to continue our wonderful and glorious work. So let us begin. So just as a quick overview, finding the domain and range of a function, again, review from last section. Domain are all your x values, range are all your possible y values. So you've got that going for you there. So domain are whatever x's I can put into a function, and the range is the resulting y values of that. So a quick review, find the domain and range of the following function here. So for my domain, remember it's all my possible x values, so I go ahead and go, okay. Remember, it's a square root. It's one of the big two, that and a rational function where I have issues. So I go, okay, the inside of this has to be greater than or equal to 0, because we can't have negative square roots. I add 3 to both sides here, and my domain is x greater than 3. Now you can use set builder notation. Now, should this be right there like that? No. Why are these different? Because it can include 3, therefore I do a bracket. Then why is this not a bracket? Because it's infinity, we can never really get there. Now for my range, remember, square root, if this thing cannot be negative, then this, the lowest it can ever be, is 0. So that's why my range is y greater than or equal to 0. Or, using my set builder notation, 0, comma, infinity. So we've got that going for us. Now with these two, just a quick note, find the domain and range of the following functions. For y equals x squared, so regular x squared here. My domain, do I have any issues with x? No, I do not. So using set builder notation, negative infinity to infinity. So if you just see this in a polynomial, it can be whatever it wants. Now, the thing is, whenever you square something, it's always going to be positive. So my range here, for just one of these, is going to be 0 to infinity. Why is that? Because x squared can never be negative. If I square a negative, it becomes positive. If I square positive, it's still positive. So this y value can never get to be negative. It could be 0 if I put 0 and square it. That's why I have the bracket here. But it can never be negative. Now, if I make transformations to it, like adding things to the end back here, then that would change my range around. But my domain here, if you just have an x squared in the problem, and it's not in a fraction, or it's not in a square root, then this domain is always going to hold true. X to the third. Do I have any problems with x? No. It's not in a fraction or a square root, so negative infinity to infinity. How about my range? Well, if I take a negative and I cube it, I'm going to get back a negative. If I take a positive and cube it, I'm going to get back a positive. So my range here is negative infinity to infinity as well. That's going to become important for us. So what that means is anytime you see an x to the third here, and it's a regular old polynomial, you know my domain and range automatically. Which is awesome. That's great for us. Speaking of functions, though, we're going to talk about increasing and decreasing here in a second. Increasing and decreasing and constant functions. So the first thing is a function f is increasing over the interval if the following happens. If x2 is greater than x sub 1, then f of x sub 1 is less than f of x sub 2. What does that mean? It means the following. If I take an x here, and I find another x bigger than it, it's increasing if my y values are also in the same ratio. So as you move from left to right, as you get bigger, your y values should get bigger. So if it's increasing as x go up, as your x goes up, so do your y values. Always the same. This is this notation from a book. So you be clear of, hey, where did this come from? But as x goes up, y goes up. Decreasing is as your x's increase, the opposite holds true. Your y values decrease. Or, as your x values go up from left to right, your y values go down. That's decreasing. And a function is constant if your y values are the same. So if you have your y values being the same, that means f of x sub 1 equals f of x sub 2, then that means you have a constant function. You could also have a function that both increases and decreases on the same graph. So here's a quick picture here. Notice it's decreasing, because as I move from left to right, my y's go down. At some point it stops, and now as I move from left to right, my y values go up. So it can both increase and decrease on the same graph, and we will work on finding exact intervals for these in the future. But speaking of our last graph there, we're going to deal with symmetry. Now, there's a lot to take in here, so should really be important on taking your notes. So, the first one is a graph of the relation is symmetric with respect to the x-axis, and you have the definition. There's a picture symmetric with the x-axis. It's like if you put a mirror right here, it mirrors itself. And what that means, algebraically for us, you replace y with a negative y, and it produces the same equation. Now, an easier one to see for us is something symmetric about the y-axis. See how it's symmetrical? You can put if I drew a line right here, the graph would mirror itself on either side. Replacing x with a negative x produces an equivalent equation. An example being y equals x squared, or f of x equals x squared. If I put f of negative x in here, I'm going to get negative x, that quantity squared, or just x squared. You see how they both are equivalent relations there? That's why x squared is symmetric about the y-axis here. And last but certainly not least, symmetric with respect to the origin, if and only if this happens. Replacing x with a negative x and y with a negative y produces an equivalent equation. An example being y equals x cubed. This is what this function shows right here. Let's replace a x with a negative x and a y with a negative y. So I have negative y equals negative x to the third. Cube a negative, it's still negative. Both the negatives here would cancel. And lo and behold, look what I have in front of us. An equivalent relation there. That's why the graph of y equals x cubed is symmetric about the origin. Y equals x squared is symmetric about the y-axis. And the last thing we're going to talk about here is even versus odd functions. So, functions that are symmetric with respect to the y-axis are called even functions. An example here being your y equals x squared. So it means if you put a negative x in, it's like if you put a negative or positive in, you'll still get the same y value back. They're called even functions. Functions that are symmetric with respect to the origin are called odd functions. So that means if you put a negative x in, it makes the whole thing negative. The example being y equals x to the third. If you put a negative in here, it makes the whole equation negative. That's called an odd function, even versus odd. This will be very important for us later on in the year in trigonometry, which even and odd plays a very key important role. But for right now, we have respect to the y-axis, it's an even function. Respect to the origin is an odd function. Thus ends this little tutorial, and you can begin working on your homework for section 1.2. Have a wonderful, happy, and fun-filled day. Yay, math.